Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Where tonight, we're going to take a look at functions, specifically maybe inverses and transformations of functions using the TI-Nspire CX. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough to teach, tough to learn concepts accessible to all my students. And tonight, I'm super excited to be joined by our two panelists, Robin Gopinski and Scott Knapp. Robin is in her 32nd year of teaching and is currently teaching Algebra 2, Trig Honors, Pre-Calc, AP Calc, BC at Highland Park High School in Highland Park, Illinois, a suburb of Chicago. She's presented at numerous local and national conferences on how to transform your classroom using fun, tastic activities, two-way meaningful learning using the TI-Nspire Navigator system, investigating rates of change with the CBR2, and bridging coding with calculus via the TI Innovator Rover. She served on the board of MECAS, which hosted the USA CAS International Conference, with the last time being held in 2019 at HPHS. She pilots new software updates, has co-authored the one-day PD workshops on leveraging TI-Nspire Rover with the math classroom, and became a regional instructor with TI in 2018. And she believes integration of technology in the classroom allows students to be actively engaged in their learning through mathematical exploration and discovery. And as of late, Robin has been presenting on, yes, you can teach calculus in algebra. So Robin, it is great to have you with us.
It's great to be here, Mike.
And Scott is in his 23rd year of teaching high school math and currently teaches Algebra 2 and AP Calc AB at Glenbrook North High School in Northbrook, Illinois, also a suburb of Chicago. Scott served as an AP Calculus reader and has been a TQ regional instructor since 2011, has led numerous workshops on TI-Nspire graphing calculators, as well as served on authoring teams for TI-Nspire and TID for professional development. Scott enjoys presenting sessions at local, regional, and national conferences on how to use technology to support student success in learning mathematics. Scott, it's also great to have you with us.
Thanks so much, Mike.
And Scott, keep that rolling. Can you talk through our agenda for tonight?
Yeah, for our agenda tonight, we're going to take a deep dive into functions and specifically two topics that we feel have a lot of nice avenues for using technology, and those are inverse functions and transformations of functions. So we're going to be showing a variety of activities and demonstrations that you can do with your students to hopefully help them connect to the topics of inverse functions and transformations of functions. The Nspire is probably the best platform that we know of that makes for a lot of dynamic learning and dynamic technology opportunities for students to make those connections, specifically with inverse functions, transformation of functions. And one of our big goals tonight is to talk also about incorporating multiple representations of functions using the technology.
Nice. Thanks, Scott. And stick around to the end because we're going to be giving away to one lucky winner a TI graphing calculator of their choice. Robin, can you talk through our expected outcomes, please?
Yes, our goals are that we want our participants to be able to utilize the TI-Nspire CX technology, preferably the CAS. You'll see us really leveraging the CAS this evening to help students engage in making those connections while learning about specifically inverse functions and transformations. The Nspire really allows us to make demonstrations and create really unique guided discovery student activities in the classroom that really actively engage students and put them in the driver's seat. So that's our first goal. Our second outcome that we hope is really to emphasize how the Nspire calculator, and this can also be done on the 84 as well. It might not be as dynamic or as clean with the connectivity that we're going to show tonight with linking various pages and a problem together, but we really want to emphasize the multiple representation of functions. Okay, and so at the end of the evening, Mike will explain how people who are in this webinar this evening can have access to the TI-Nspire software for a 3-year trial for free. So just keep in mind that even though your students may not have this handheld, they can have access to it on the icon on the Chromebook, on an iPad, or you can utilize the software to demo as the teacher, which is often what we do in addition to having kids be in the driver's seat doing this on a classroom set of handhelds.
Awesome, Robin. Thanks so much. Some of you already realized that we're going to be using that chat window tonight to send general messages, and so many of you have already given a quick shout out as to where you're from, and it's really cool again to see just how diverse our audience is all across not just the United States, but the world. We'll be using the the Q&A window tonight. If you have any questions for Robin or Scott, and I think they intentionally have put in certain pauses throughout their session tonight to get some of those questions answered. So if you have them, please feel free to get those questions asked. I know they will do their best to get those questions answered live. And as a reminder, the session is being recorded, and we will provide a link to the event certificate of attendance at the conclusion of the webinar. So Scott, it's all yours.
All right, I'm taking over here. Mike, it's asking me to have you close the poll and change the presenter. I don't know why it's not just handing it to me.
Okay, sorry about that. Give me a few seconds here to take care of that.
All right, I think we're good now. You got me on your screen?
Yep.
Okay, so as Mike talked about, please feel free to ask questions in the chat. When I'm speaking, Robin is going to be taking a look at that chat and vice versa, and we'll do our best to address all of your questions. We also have a lot of resources to share with you tonight. So as we move through things, you might be like, oh, I want to see how they did that again. We've actually got a document that we've created that kind of walks you through some of the steps of what we're going to show you as well, and we'll be sharing that with you. So, feel free to ask questions, but also know that you'll have some resources available after our presentation. So I'm going to lead us off talking about inverse functions. And one of the things we thought would be a great idea here is to talk a little bit about how would you introduce inverse functions, because neither one of us thought that technology was the best way to do it. Sometimes the technology exploration is the best way, and then to show where technology kind of fits into the topic. So this is a lesson that's real fresh to me because I just gave it yesterday. And typically when I have students start thinking about inverse functions, I want them to understand the purpose for having them. So I kind of go back to something that's familiar to them. They've seen a formula before in their previous math or science classes where they've converted temperatures from one degree type to another. And in this case, if they were going to Toronto for the weekend, they might look at the weather forecast and think, oh my gosh, it's going to be really cold. But if they use the function f of x equals 9/5 x plus 32, they quickly find out that, oh, that's actually 68 degrees Fahrenheit. Not so bad. Not so bad at all. But then I kind of turn it around on them. I'm like, well, what if you have somebody visiting you from Canada and they have the reverse idea and they look at that temperature and think, oh my gosh, 50 degrees, that's going to be blazing hot. But they realize, oh, wait, that's Fahrenheit. Well, if we want to use our initial function, f of x, that 50 really is the output of that function. And so having the students kind of walk through, well, how would I find out that number that gives me 50 out? And this really drives home the idea of what an inverse function is. It's undoing the operations so that we can have the inverse relationship. So the first step is to subtract 32 from each side. The second step is to multiply by 5/9 to each side. And in the end, we can get our temperature converted into Celsius. And then hopefully the students realize that, okay, now if we're talking about the temperature x degrees Fahrenheit, that we need to subtract 32 first and then multiply by 5/9. So I like an activity like this that doesn't necessarily use technology to address the purpose behind why we have inverse functions, and also to start building the idea of how do we construct an inverse function. So at that point, though, I think that's where technology really can be useful. And Robin's going to take over here and show how you can use technology now from here, now that we know what inverse functions are and why they're important. So Robin, go ahead and take over.
Thanks, Scott. So as Scott said, you know, the idea of inverses or opposites is just very important in mathematics. And, you know, the word is used in different contexts, such as additive and multiplicative inverses. So the rules governing the reversal themselves can be functions, and sometimes they're just relations. But the most difficult part, what Scott said, is for kids to understand the concept, not just the doing. The switching X and Y and solving for Y is often how kids view an inverse without doing a deep dive, which is what we hope to do with you this evening. So actually, before I start, I usually have a conversation following something like Scott said, introducing the whole idea of inverses, and then asking them if they can come up with an inverse parallel in their own life. And it takes a little while, but they do come up with some great examples. Like, you know, if I'm putting on my sneakers, I first put on my shoes, then I tie my laces. And then at the end of the day, I untie my laces and I take my shoes off. Or wrapping a gift. I wrap a gift, put the paper on, then I put a ribbon and a bow. And then when we unwrap it, we undo the function. And so having kids come up with any kind of applications of inverses is invaluable. Okay, so on the Nspire, one of the beauties and advantages of this over the 84 is that we can link the pages within a problem. So we're going to go ahead and we're going to continue where we left off from Scott's example with the two functions, the Fahrenheit function equation and the Celsius function equation. And we're going to go ahead and store those on a calculator page. So you can go to menu actions and you can define that Fahrenheit equation, and we're just going to go ahead and type it in. I like to have my students use the fraction feature built in to the calculator. Sorry, X was 32. It's going to say done when it's stored. Another way a lot of my students like to do it is they like to do the control hit the math template. The colon equal also will store that function for your students in the same way that the word define will. So giving students options is always a great idea. There's more than one way to do things on the Nspire. All right, so just showing the input-output relationship, you know, inputting 10 degrees Celsius, giving an output of 50 degrees Fahrenheit, or inputting the 50 degrees Fahrenheit, getting an output of 10. These are really important for students to see these connections, to see how the point is inverted, okay? And so I like to always toy around with that first. So multiple representations, and you see that in NCTM standards, Common Core, state standards, College Board talks about the rule of 4, and we're going to really try to do that in a deep dive with inverse functions as well as transformations, and really making a lot of connections because Algebra 2 is the study of functions. And so I started off just kind of giving an algebraic approach here. I like to transition now and show the connectivity between these pages, doing it numerically and graphically as well, okay? So I'm going to go ahead and add a page, and I'm actually going to add a graph page right now. And what's beautiful about the Nspire is these pages are linked. So I'm going to go ahead and insert for the first function we graphed, the f of x function that I previously stored. And then I'm going to hit tab, and I'm going to go ahead and store our Celsius function equation. Okay, and I'm going to go ahead and split screen because first I want to show them the multiple representation, the numerical representation. And to do so, I hit Control T and I can split screen. Oops, sorry. And here is the table. So they can see the input, they can see the output, and if I scroll to the right, they can see the output in the Celsius equation. But it's really hard to see on the split screen. So if I hit Control 6, it's going to go ahead and slide the table now to its own page. And this is usually much more readable for the students to see what we want them to see about this relationship with inverse functions. And so now in this workspace, if I hit menu, the options have changed. And what I'd recommend in this case is I go down to table, edit table settings, and I can just keep the table stuff at 1. But what I really want to do is change the independent, the input, to be in what we call an ask mode. Okay. And so here, if I go ahead now and I input 10, notice I can see the relationship in the Fahrenheit equation. It comes out inputting 10 gives me 50 degrees Celsius. And if I input 50, I can see the output over here is 10. So this is another great visual representation for the kids to see the relationship between the inverted point on inverse functions, okay? So now I'm going to go back to page 1.2. Let's take a look at it graphically. So we looked at it algebraically with the functions and inputting. We looked at it numerically. Now we're going to look at it graphically. All right, so I'm hoping that I'm going to show you some neat features on this. If you go ahead and you pull down on the axes, I can bring it in and I can adjust it so that those functions fit on the same screen. And I'm just going to go ahead and slide these functions out just so that we can see what's going on in here with the two lines. All right. So a great guided discovery activity is now to graphically show them the points, how they're inverted on the two graphs. And if you hit P and you go down for points by coordinates, and I can insert 10, let's have that be a consistent input. Make sure you hit enter. And then I want to insert that 10 into my F1 function. And notice the calculator will go ahead and show that point A as 10, 50. Now I can hit P again and go points by coordinates. And I can invert that point by doing 50, enter, and show that value on the other equation. And so here they can get a visualization with the graphs with the 2 points being inverted. Okay. All right, I'm going to go ahead and I'm going to delete these points because what would be really beautiful is that they didn't just see maybe 1 point, but they saw a collection of all the points sliding if we create a slider. And so that is one thing that we can do, leverage with the Nspire. So if I go back to points by coordinates by hitting P, I'm just going to go ahead and enter A, and then I'm going to go ahead and put F of 1 of A. All right, and I'm just going to go ahead. I have a point here, and I'm going to create a slider that allows me to move this point up and down the line. All right, so if I hit Control Menu, I can go ahead and change the settings. And so I'm going to go ahead and change the settings so that we're going, we'll start with a value of 1. We can go -50 to 50. We'll go step size 2. And I'm actually to make this vertical so that it's off on the side of my screen. So I kind of have an idea where I'm headed with this with you all. Okay, so now I can go ahead and I'm going to just slide this up and have it off on the side of my screen. Now I want to link this page, this point with the inverted point on the inverse function. And so I'm going to go ahead and hit P and do points by coordinates. And I'm actually going to go ahead and invert this point. And notice that it graphed beautifully on the other one. All right, so I'm going to just slide the labels a little bit off so you can see this. I'll slide these points out, the order pairs. All right, so now if I go ahead and I just use the slider, you can see how the points will move up and down the lines, and you'll see how they're linked, and the X and Y's in fact switch. So they're discovering this relationship versus, you know, saying at the beginning of a lesson, they're discovering that inversion of the X and Y coordinates and the relationship on their own. What's neat is you could take it one step forward and really connect it to geometry. A lot of Algebra 2 students take geometry before they get into Algebra 2. And so any chance or opportunity you have to connect it with prerequisite knowledge is always great. So one thing you can do is we really want to get to the whole idea of the mirror line and the reflection over the 45-degree line y equals x. And so if I go down to geometry and I go to points and lines and I go to segment, I can go ahead and connect a segment between A and B. Okay, and then I'm going to go ahead and hit menu, go down to geometry, and I am going to go down to construction, and I'm going to put a midpoint in the middle of that segment. Okay, and I can go ahead, I'm going to actually, to really accentuate what I want to see happen, is I am going to go ahead and change the color of that midpoint so you really can see it. And I'm going to make it green. Okay. And now what I'm going to do is I'm going to hit menu and go down to trace and down to geometry trace. I'm going to click on that point and then hit my slider. And now it's going to create a beautiful example going up and down of locus of those midpoints, okay, that are equidistant between the 2 points on the function and the inverse of the function, okay, going up and down. And if still students are struggling to see that this is the perpendicular bisector, have them prove it, okay? Have them take it a step further and have them take the menu, go down to geometry, and have them measure those pieces, okay? So have them measure from A to the midpoint, place that value here, then measure it from here to the midpoint, place that number there. And so they're seeing that equidistant, right? That's what we want them to see. We want them to make the connection to the perpendicular bisector theorem. And then I also would encourage you to have them, go down to geometry again and go to measurement and measure that angle. Okay, I'm sorry, I just lost that. Okay, menu, geometry, measurements, angle. And I would pick like a point here, the midpoint, and point B. Okay, and I'm just going to go ahead and drag that label and put it in here. You see the little angle arc there, so indicating what's happening. And now when I go ahead and I use that slider, we're seeing that relationship that if a point is on the perpendicular bisector of a segment, that it's equidistant from the segment's endpoints. And this is a really neat connectivity for kids to get a visualization of the beauty of that reflection, okay, over the line y equals x. Now I'm going to hand it back to you, Scott, so you can go ahead and take this further, one step further with inverse triangles.
Yeah, inverse triangles. I don't know, Robin. I might have been the person who coined that phrase. I'm not sure, but inverse triangles are kind of a way I get my students. This is my lesson tomorrow, so it's crazy that this has fit right into my Algebra 2 class this week. Tomorrow we're going to learn the properties of inverse functions, and the first one being the graphing property that Robin just illustrated. And what I typically like to do is I like to talk about inverse triangles. So before we jump to any technology or anything, I have my students graph a triangle, any 3 points, and the conditions are mainly, I pretty much want it to be scalene and spanning a few different quadrants. I don't want it to have any symmetry over any of the axes. And I try to get them, challenge them to come up with something that's a little bit, not quite so equilateral or isosceles. And then I ask them to convert each of the points of their original triangle to the inverse of each coordinate pair and to replot that. And sometimes, just one pair of triangle and inverse triangle isn't quite enough. So I have them actually do it again. And they end up having a couple of them. And they're in groups as well. I do a lot of group work with students. So they're kind of looking around at each other's as well. And hopefully that's giving them a pretty good glimpse. But if not, then we bring in the technology. And so let me pop that up. And I actually have it set so that if they drag the triangle on the left, the one that's in blue, A, B, C, it will actually simultaneously plot the inverse triangle, is what I've been calling it over the years, the inverse triangle. And if they click on this slider right here, and they don't know what that slider is even there for till I tell them, they get a line. And we talk about how there is some symmetry here. And I think they realize that, but where is the symmetry? Because most of their math has been, symmetric about the X or the Y axis, but here it's not those two things. So I challenge them to try to move that line to become the line of symmetry through the two graphs, and then to come up with the equation of that line. And hopefully they recognize, oh, this is very easily written in slope-intercept form because the y-intercept is 0 and the slope is 1. And that's the line y equals x. So we kind of start with inverse triangles. I also like what Robin showed as well, maybe even after that, just to kind of go back to geometry and make that connection. But we typically start with inverse triangles in my classes. The next thing I want to show is kind of just another way to look at inverse functions and the graphs of them using the geometry trace feature. So I'm going to open up a new graphing page right now. And I'm going to enter, let's mix it up just a little bit. I'm going to enter an exponential function. And my students haven't really studied those yet this year, so I don't know that I would use this tomorrow if I were doing this, but it's just a different function type. And on that function, or on the screen, I'm going to then plot a point that's on that function. And Robin showed this feature earlier. If I press P on either my handheld or my teacher software, I can go to point by coordinates, and I can tell it I want the coordinates to be at A. Now, A is going to end up popping open a slider because it doesn't know what A is, but right now it's going to be A and then F1 of A. And that's going to plot a point here on the function to wherever the current slider value is set, which is A equals 1. I'm going to go ahead and change the settings on that slider. I right-clicked on it on the teacher software. That's Control Menu on a handheld. And in the settings, I'm going to change it so that my step size, I think it's going by ones is the automatic step size, but 0.25, because we're going to do a trace here in a little bit. And then I'm going to go ahead and minimize that slider. I'm going to move it up here. So right now, what I've got is I've got a point that's on my function y equals 2 to the x, and I can change the value of x based on the parameter called a. So next thing I want to do is I want to plot the point that would be the inverse of that point. So not 1, 2, but 2, 1. So again, I'm going to press P so that I can access point by coordinates. And this time I'm just going to reverse what I had entered the first time. So F1 of A will be my input and A will be my output. And we see that inverted point. And I'm going to go ahead and change the color of it here. So if I right click or control menu on that point, I can change its color, and I'm going to change it to be red. And I kind of like that because now I can kind of distinguish them a little bit. But what we're really watching right here is the tracing, so to speak, of the inverse function, which we know as teachers who've taught this before to be y equals log base 2 of x is what it's tracing there. So that's kind of nice. Now, if we want to get kind of a little bit more of the locus of all of those points, if I hover over the point on the inverse relation and I right click, I can perform a geometry trace on that point. And if I now click on my slider, it will trace the locus of points now based on what the slider value is. And so I can see the inverse graph, which is a function this time. And I also can see that that's a reflection over the line y equals x, if we would type that line in there. So that's kind of a nice way just to reinforce that graphing relationship. I like to kind of change the colors up a little bit. A lot of these things I'm doing as demonstrations for my students or have already pre-made for them, so they don't have to spend time with all the constructions. But what I like about this is I entered a function into F1 and I chose an exponential function. But what if I had chosen something different? Well, I'm going to click here and erase my geometry trace. And I'm going to go back to my function entry line. So I'm going to press tab until I get that open. And instead of y equals 2 to the x, I'm going to try something a little bit different. How about y equals x squared? And now I have the same thing. Now notice my slider is a equals -5. So that point has slid off of my window. So let me bring it back in here. But now I have a dynamic document that will work for any function I decide to type into F1 of x. I don't have to recreate that again. And so again, I can have students watch the tracing of the inverse relation, which here we know is not a function, x equals y squared, which our students study in pre-calculus when they get to conic sections. But it's pretty nice to be able to change that function and see all kinds of different inverse graphing relationships. One last thing I want to show on this slide before we move forward is you can actually plot the inverse of a function, which may or may not be a function. And you can do that by accessing a text box on your screen. So the easiest way to do that is if you're hovering over your page and right click, one of the options in the drop-down menu is text. And remember, my function was y equals f1 of x. So the inverse relation would be x equals f1 of y. And when I type that on my screen, nothing's going to happen. But the Nspire, if you take that text with the inverse relation and drag it down to the x-axis, notice how it actually plots that inverse relationship. And it's right now fitting over my geometry trace, which is what it should do. And so if you just drag it over there and then just drop it there, now you actually see the full graph of the inverse relation. And so that's kind of a nice feature as well that you can use on the Nspire. So those are a couple of ways, and Robin and I have both shown ways of kind of working with the graphing property of inverse functions. Next up, Robin's going to take us through a couple of exercises to look at the composition property.
Thanks, Scott. That was really cool. So the composition of functions is very, very important because one of the ways in which we ask students to verify that equations are in fact inverses of each other is for them to satisfy the composition of f of the inverse of x is in fact equals x, that they undo each other and you end up with the input. And so you can do that either way, right? Like an f of g of x or g of f of x. And this is something that's very important even at the calculus level. And so spending some time on this at the Algebra 2 level really lays the foundation really well for what follows. And so if we go back, let's go ahead and we're going to look at that whole idea through 3 different representations. And so we'll first go ahead and look at it through the algebraic representation. So if we go ahead and type in f of x to get our Fahrenheit equation, we can see that if I type C of, and I go up and grab that Fahrenheit equation, and I input it, that the output, they in fact undid each other, and the output is x. If I go ahead and I take a look at C of x, and I go ahead and I insert that into the Fahrenheit equation, notice once again, they undid each other. Okay, and that's that reversal that we want them to see. So the f of C of x is a feature, something that we can demo on the Nspire CAS that can't be done on the non-CAS, so to speak. I guess that's what we call it, the non-CAS. So we can see that inversion and that composition and verify the equations are in fact inverses of each other. And you can, take it a step farther and just show that when you're undoing it, you come back to that input that you started with. If we take a look at it numerically, let's just go ahead and we're going to define a third function. And let's have that third function be equal to f of C of x, okay? The one composition going one way. And then let's go ahead and define a fourth function to show the reverse composition. Okay, so we're going to define both of them. And remember, these pages are all linked. So this is stored in here, and I can have access to it on the same spreadsheet, which shows that numerical representation. And I can go ahead and drop down and change these functions in each of the columns so that now I'm taking a look at when the input is 10. Notice that the f of c, when they that composition satisfies that composition with them resulting back into, with the result or the outcome being the input that we started with. And this is like a really beautiful representation. If we took a look at it graphically, these values, f of 3 of x, has stored each of the compositions. And so if I go ahead and I hit the tab button and I go up to f of 3, it's stored there, but it hasn't graphed yet until I hit enter. Okay, and so you can see that the line is graphed right there. And if I do it again, hit tab, oops, sorry. If I hit tab and I go up to f of 4 of x and hit enter, here that the students can see that both of the functions, both of the composite functions graphed on top of each other, which was that 45-degree line of y equals x. So it's just a great visual for them to see through 3 different representations that composition of functions, of the inverse functions. All right, Scott, do we think we have time? Should we transition now to the transformations of functions?
Yeah, I think we're right on schedule, which is great. So we're now going to move to transformations now. I think we've shown you a variety of ways to use the technology to dynamically help bring some life to inverse functions and their properties. So let me pull up my screen, and we're going to start off with the first transformation that I do, and I'm guessing that's probably similar to what everyone else does, and that would be with translations. So, and again, one of the things we want to emphasize here is not just using the technology to see things, but also the idea of the multiple representations. And we're going to show you ways that you can effectively do that related to translations of functions. So for translations, I'm going to first of all insert a new page, and I'm going to insert a graphing page. And typically the function I use for translations is the quadratic parent function, y equals x squared. Not sure why, it's just been the one that I've always used. So I'm going to press enter on that. And I'm going to tidy things up on the screen just a little bit. I'm going to move that label. And I'm going to right click, which on a handheld is control menu. And I'm going to change the attributes just because I want that to be dashed and kind of not in the background, but just not the major focus of what students are going to be looking at. And that's one of the things that we can really do with the Nspire is all the different colors and different sizes of things. And I know that's similar to what can be done on the 84 too, but I think it pops a little bit better on our screen on the Nspire. So next I'm going to enter a second function. So I'm going to hit tab so I get my entry line. And I'm going to type in F1. So notice it went bold when I did that because it knows what F1 is because it's in the line above it. And in parentheses, I'm going to type X minus H. And if you've seen us do things like this tonight, you're probably thinking, okay, when he clicks enter, it's going to ask him if he wants to create a slider because H is a new parameter. And so I do. I want a slider called H. I kind of wish they would default show as minimized, but I'm going to go ahead and go into that. I'm pretty happy with the settings on H. I just want to minimize it. And now what I've got is a dynamic way of changing that value of H and seeing how the graph, in this case, translates horizontally, right and left. But even better, if we're looking for multiple representations, if you look at this label here that I'm moving on the screen, notice it says F2 is F1 of X minus H. I can actually right click on F2's graph and go into the attributes. And if I slide down to the fourth option, I can actually label the parameter, meaning if there's a parameter in there, which we have one called H, if I slide to the right, it will then drop that parameter into that expression. And so notice it changed from H to 2, which is what H's current value is. And that's kind of nice because now that gives us a second representation of the function. We see graphically how the function is changing, but we also see algebraically how the function is changing. I'm going to go ahead and insert a second, well, not insert a second slider. I'm going to go back up to F2 and I'm going to add in plus K just so we can have that second slider. And this time I'm going to go to settings and I again want to minimize it. This one I tend to like for it to be vertical just so students can kind of connect the dots a little bit better, that this is a slider or a parameter that changes things vertically here. So a nice way to have a couple of different representations on our screen at one time. Now, just like I showed a little bit earlier with the inverse tracing, this is now a dynamic document where I can change what F1 of X is. And the way I've linked everything, it's going to then change just to that new parent function. So you could get as creative as you'd want. Maybe you want students to look at the cubic parent function. And so if I go and I change F1 of X to X cubed, we can see how transformations look and work. And it's ideally the same for the cubic parent. Or we could go back and use the absolute value function. So I'm going to type abs of X because the computer or the calculator and computer know that that is absolute value. And so we see the absolute value parent now translating on our screen. So once you've had it created once, you can reuse it so many times in so many different ways by just changing that function entry that I initially had in F1. Okay, so that's a little bit with translations. Transformation number 2 typically involves reflection. So let's take a look at some of the things that we can do there, again with the idea of multiple representations in mind. So for reflections, I'm going to again insert a graphing page. And for reflections, I typically like the square root function because I don't like y equals x squared or the absolute value of x because of the symmetry that it already has over the y-axis. So I try to pick a function that doesn't have any symmetry. So this would probably be the best one for them to be considering at this point in our year of Algebra 2. So I've got that graph on the screen now. And now I'm going to enter a second function. And remember, reflections are really multiplicative changes to the function. So I'm going to take a, which is typically the variable we use outside of the function, times f1. And notice f1 went bold because it's recognizing f1 from the previous function line of b times x. And as you've seen before, you probably are thinking maybe to yourselves, hey, it's going to ask him if he wants sliders for A and B. And so I'm going to get that message. And I'm going to say, certainly I do. Again, they're not quite to my liking. So I'm going to go in and change the settings on those a little bit. I'm going to actually go from -1 to 1 because in this activity, I only want to really look at reflections. And so my step size is going to be 2. That way it can change from 1 to -1 and from -1 to 2. And that's all that it can do because I don't want to throw in anything involving dilations quite yet. This is just looking at reflections. And same thing for B. So if I go in there and change its settings, I'm going to go from -1 to 1 by 2. And I'm going to minimize that as well. And so those are going to be both up here. I'll put this one up over here on the upper right. So, and one more time, what I'm going to do is go back and change so that I can see those parameters. If A is 1 and B is 1, it would look a lot nicer in this label if A and B were actually 1 in there. So if I right click, now notice here, you got to be careful. I think it's going to take the one on top. So graph F2, make sure that that's the one that we're right clicking on. And I'm going to change the attributes of that so that we can see those parameters. And so it's kind of nice because, again, we've got the multiple representations. We see that when A is -1 or we're multiplying on a -1 to the outside or output of the function, that's a reflection over the x-axis. And vice versa, if we're multiplying the inside by -1, that's a reflection over the y-axis. And then we also have what I call kind of the double reflection if they were both to be negative. And this is great, but for thinking about multiple representations, there's still a little bit more we can do. So what I'm going to do is we see this graphically. We see it by its algebraic function rule, but it would be nice if we could see the relationship numerically as well. So I'm going to plot a point on f1 of x, and I'm going to pick just one of the nice integer pair points. And I think the best one maybe for this would be 4, 2. So I'm going to press 4 enter and 2 enter, and it's going to put that point down at 4, 2. And what I want to do next is I want to plot the corresponding point on the transformation, which we know is at 4, -2. And I want that so that it will change no matter what the slider values are. So I'm going to go back to P and point by coordinates. And here's where we have a little bit of understanding of what's going on. We know that that B value is really something we divide off the X coordinates. So I'm going to do 4 over B. And the A value is something we multiply times the Y coordinate. And so 2 times A. I usually save the idea of dividing by B until we get to dilations in my class. But that's technically what we've got there. And what we now have is that transformed point. And so we have 3 representations on our screen at once. We have the graphing representation of the reflection. We have the function rule or the algebraic. And then we have the numeric, seeing how the coordinate pairs change. You know, in this case, if we take a look at what's on the screen now, when the inside of the function changes signs, that changes the sign of the x coordinate on the parent function when it's transformed, in the case of B being -1. So 3 representations on one screen. Pretty powerful stuff. Robin's going to come in next and show us a little bit about piecewise functions and dilations, and then we'll be getting kind of close to the end, I think.
Yeah, thank you so much, Scott. So, you know, a lot of the features can still be applied for dilations, just like Scott showcased. But we thought might be a little different was to showcase piecewise functions in a dilation with sliders. And so that's exactly what I'm going to do. So I created a new document while Scott was presenting. So it's not linked to the previous work that I did with inverse functions. And if I go ahead and hit the math template button, you'll see the icon right here is for piecewise functions. And it says, how many pieces you want. I call them branches, but I want 4 pieces. And what's really nice about doing this is if you want to create something where you're teaching, like as a preview about periodic functions, you could actually fill up the whole screen and really showcase the power of this feature with piecewise functions, with having kids do that as a preview before they do trig functions, trig function graphing. All right, so if I want to go ahead and create the branches, I'm going to go have the first branch being 1, and I can have it go from -4, and I could use the control equal and use the inequality features built in, or the calculator also recognizes if I just want to do less than and equal to -2, it will recognize that as less than or equal to. Okay, so I do have some options here, and I wanted you to be aware of that when I'm typing these in. So I'm just going to go ahead and type in several functions here. And I will do, let's see, equal, let's put in, whoops, yeah, control division, -5/2. So I pre-worked out a piecewise function here to really kind of showcase the beauty of the Nspire with these. 2, and let's do this one up to 6. So you can see when this goes ahead and graphs, the calculator go ahead and translates the inequality signs, okay, to what we like to see. And I'm just going to go ahead and I'm going to hide this right now because our focus really is on this piecewise function graph and focusing on dilations. And so just like Scott had showcased, I also changed this. So the parent function, I like to make the line dotted so it's in the background and you're always referencing that. And then we can go ahead and we can go to tab, and just like Scott showcased here earlier, we could do F times F1 B times X. Okay, it'll create those 2 sliders. And this one we know is a vertical stretch or vertical shrink. So I will also adjust the settings. Okay, and we can go from, we go, let's see, -0.5 to 2, just so that keep this on our screen. And because this one does the vertical stretch or shrink, I'm going to go ahead and also change that to be a vertical slider. Subliminal there for students to see that representation. I'll slide that up there. And I will change this one. Settings. Let's see, let's just do the same thing. 0.2, 0.25. I'm going to keep this one horizontal because we know this is doing affecting it horizontally, compressing it or stretching it. And so we have these on here. Whoops, sorry. Just adjust my settings. Okay, there we go. So that's within my. Okay. All right. So we got this set. I'm just going to go ahead and I can slide it in a little bit if I want to magnify it. Oops, sorry, I'm having little technical issues. I'm going to try to hurry because I know we have some really cool stuff we still want to show you. Anyhow, I'm just going to leave it right there. So I could also go ahead, I could click on that function. I'm going to put the values to showcase in the equation as well. Hold on a second.
Yeah, you have the function equation highlighted as well. There you go.
There, yep.
You got it.
Yeah. Okay, so now they're inside here. Let me just slide this into the corner. Okay, and so now if I go ahead and I hit those 2 sliders, I'm getting a really cool visual here of the dilations. Okay, and we can keep going with this so kids can also see that reflection as well. So I just want to showcase the piecewise function in case you weren't aware that's something really cool that you can do on the Nspire as well. Scott, you want to go ahead and show some of the pre-made Nspire transformation documents that you pre-made that we're going to be sharing in the Google Drive at the
Sure.
end.
Yeah, for all of your wonderful participation and being a great audience, we've got some nice parting gifts for you tonight. So we're going to be sharing a link to a Google Drive folder, and let me show you kind of what you're going to see in there. Oh, just a second. I've got to re-sign into my Google, so I'll have to come back to the folder in a little bit because I have to do a two-step verification because of my school. I don't know if anyone else understands what that means, but one of the things I've done is I've created some files, and I'm showing you kind of on the screen right now, and these are going to be in that folder where there's a student activity worksheet, and students complete that worksheet and learn about each transformation. And it has the multiple views all on the same screen already preset for them. So they can come in and just quickly manipulate the sliders and make some observations. And there's a lot of questions that they're asked kind of along the way that address both how does the graph change, how did the coordinates change, how does the function rule change, and they can see those multiple representations. And I have an activity for each transformation type. So for the translation, I have the quadratic function. For reflections, I have the square root function like we talked about. And again, you see the multiple representations, the algebraic rules up top, the coordinates or the numeric changes are here in the middle box, and then to the right is the graph. And again, I have that also for dilations as well, of all types. So for A being bigger than 1, and then it goes from there to A being smaller than 1, and all of those we're going to be giving to you. I am going to try to get logged back in here so that I can show you that. That's going to take me a second. Sorry about that. It times out after 12 hours, and looks like I got into work this morning at 7:45.
And what's really neat about Scott sharing these pre-made TNS documents with you is we really utilize them as guided discovery. As Scott alluded to, kids are working with a partner, they're working in small groups, and they're making these connections and discoveries, and you bring the class back together and they're coming up with the rule or the formula, the definition. They're writing it based off of their discoveries. They really, really, really love playing hands-on with these different activities and documents.
Yeah, so let me just pull up kind of what one of them might look like. So for example, in this folder, the transformation activities, you see the TNS files, those are the calculator files. And then the PDFs are all the different student activities that kind of take them through and refer to different pages on the Nspire and how they need to change the parameters. And again, getting written down the different multiple representations, how the function rule is different, the graph will look different, and how the coordinates are different. And so those are activities that you're welcome to use, and please use and give them a shot, because I think they were really great for my students over the years in influencing the idea of those three different representations. Also in that folder, just to show you, we have some of the other things we talked about tonight. So there is a subfolder with inverse triangles if you want to try that activity out. I put it in there because I'm giving it to my students tomorrow, and it has that inverse triangle calculator file. And then we also have a link to our PowerPoint, but we have a file here, this Inspired Functions Webinar TNS that I put together that has kind of screenshots of everything that we've done tonight. So as we were working separately, we were doing a lot of different things, but if you kind of want to go back and look at some of the things and take a look at the different sheets and what are on the different pages, that's in there too. And then last, we also have this document here that is a PDF that shows kind of the different steps of the different things we were doing tonight with some screenshots as well. So it shows you kind of the key press to get through it, the instructions on how to create it, as well as kind of what it looks like in the different stages as you go. So please feel free to use that as well. We're happy to share those things. Robin, do we have a second maybe for a little bit of a bonus, a CAS bonus? You think
let's go for it, Scott.
Let's do it. So one of the things, and Rob and I love to show this, we've done a lot of work with CAS. So we love to talk about CAS, the computer algebra system. And there's some really great things that you can do with it. A lot of people aren't aware of how to use it to their advantage. They're more worried about what advantage do my students have having the CAS tools, but really it's about how can we leverage them so that they can use CAS to learn more about the math that they're trying to do. And that's a big point of what we want CAS to be. But I was always thinking about how do I best show my students that, you know, if we add that K parameter to the outside, that's a translation up. But horizontally, it's not the same thing because it's subtracting the H parameter. And my students often left a little either confused, or where I didn't want them to go was, I should just memorize everything and realize that it's going to be opposite of what it looks, but not really having an understanding of why. And same thing's true for your dilations. If we multiply the outside by a factor of A, it dilates vertically by that factor. But if we multiply the input by B, it doesn't dilate horizontally by B, it's by a factor of 1 over B. And again, my students, a little confusion. And I don't want them to memorize things. I want them to make sense of it, because memory sometimes fails in the long run when you're trying to memorize so many different things. So if we just pull up a quick CAS page here, and I'm gonna go to a new document, and I'm gonna insert a calculator page. One of the great tools that CAS has, and this is something I would just show my students as a demonstration. It's not something I would have them do on their calculators. If you go into the algebra tools, there's a solve tool. And the real reason we're not seeing those transformations, or why they're looking so different, is that we're always looking at functions from Y's perspective. Y equals. You know, functions are kind of a Y-centric world, I say sometimes. So if we want to look at them and look at the changes that are happening to the input variable X, we kind of need to solve for X and recognize what it is as a parent. So if Y equals the square root of X, X equals Y squared is really the parent function, or in this case, non-function, unless you restrict the range, which notice that command came in there. It's really X equals Y squared. So X is whatever Y squared is. So if I now go back and I do solve Y equals the square root of X, and in this case, let's do -2, and I solve that for X, we can compare the two and realize, oh, X in terms of what it was before was Y squared, but I'm adding 2 on to that, which would mean if I'm adding 2 onto an X coordinate, that's moving me right. And same thing if we would solve Y equals something like the square root of X plus 5 for X, we see that X was what it was before, Y squared, but we've lost 5 off of the coordinate. And finally, the great thing about CAS is you can do it all symbolically with variables. So if I go X minus H, which is pretty much the standard in the textbook world, we find out that X is actually Y squared plus H. And so that's why it's actually moving to the right when it's X minus H. And I'm just going to kind of jump ahead here because I already have them done. But the same thing is true with dilations. And so I've done that here on the screen here, where I first solved for X in terms of Y. And then notice that if we have Y equals the square root of 2X, it's really what it was before X equals Y squared, but we're dividing by 2. And if it was 1/3 X, we're multiplying by 3. And in general, if it's B times X, we're dividing by B. I typically use the square root function because it's one where students actually can solve quickly and easily without the technology, and they may connect to it better as far as what the CAS is doing. So that's just a little bit of a bonus from us tonight, just based on a lot of our work with CAS. I want to real quick share that link to you in the chat, and then Mike's going to have kind of a wrap up for us.
Hey, Scott, I just did, but you're welcome to put it in there again. I did while you were presenting.
Oh, great. So Mike, why don't you wrap us up then?
And Mike, people want to know if they were late, where it's going to be the video link so they can watch it at a later time.
Yeah, that's a great question. It's going to take a couple days to get everything put together, but we will have an automatic email going out to you with links to the documents, links to the recording, and links to the certificate as well. So that should be coming to your email inbox within a couple days. But it can also be found in a couple days on our website on the on-demand webinar page. Wrapping things up tonight, let me take control back from Scott. Our lucky winner is Brandon Northcutt. So Brandon, start thinking about which TI graphing calculator you want to receive, and I'll be reaching out to you very soon to get that information. So congrats, Brandon. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents that were used tonight. I messed up a little bit and I downloaded Scott and Robin's documents instead of just using the static link that they wanted me to. So I'm going to fix that later tonight, and that will be ready tomorrow as well. So in case you missed their Google Doc link, you can also get that link tomorrow from my documents link. And if you want this on demand, go and copy that link into your favorite browser to receive your certificate. And with that, I think it's just a huge thanks for Robin and Scott for everything they put together for tonight. And also a huge thanks to everyone else for joining us. We really appreciate it, and hope to see you back online next week. Have a great night.
Thank
Good night,
you.
everybody.